the whole overview of a BMX process. We'll talk about a few other things like one-sided volume, volume analyses, section mass properties, pairs clearance. If you have run a Creo simulate analysis, how can you use that? How to run like an Excel analysis. We'll also see something called a performance monitor, which kind of like tells you how a certain parameter is performing through the analysis. We'll also try to impart motion analysis, run sensitivities, and optimization. So we have a whole list to cover. Hopefully I get it done in about an hour and then leave enough time for questions. And before we get started, Rosalinda is going to run a little poll. If you guys could please get through that, and then we can get started.
We have one more left. Okay, it's all yours.
Alright. So one thing about BMX, can BMX solve complex problems? Yes. Is BMX complex to use? No. Do you need to know a whole lot of theory or whatever to run BMX? No. So the point is, the tool can do a lot of complex things, but you don't have to work as hard to do any of these complex things. So first and foremost, we're going to talk about like a BMX process. Here we start off with a little bicycle assembly right here, and what I'm trying to do over here is to basically try to position the center of gravity of this bicycle at a certain location that I want. Okay, so I'm going to go ahead and turn on the features. So you can see that you have your arms over here, you have your body, so the weights are, the forces are acting at both locations. So first and foremost, we go ahead and run a mass property analysis to figure out where is the center of gravity of this assembly. So get into analysis, mass properties, and you can see it kind of throws in that little coordinate system as to where the center of gravity is. Now you can also go ahead and save it as a feature, say mass prop, and if you go into this little tab right here, you can choose to create a point at the center of gravity, and it will also create these parameters for you. Alright, so that's where our center of gravity is. Now let's figure out where you want your center of gravity to be. Now I want my center of gravity to be between this plane and this plane. You can see the planes are at the position of the axis. So I'm going to go ahead, create a plane real quick. So I want to position right smack in the center. So I can just stick in a little relation saying that I want it to be right between those two planes. Alright. Now second thing we're going to do is to measure the distance. So I want to measure the distance between that plane and that point. So as of now, the distance is 3.2. So I want to go ahead, save it as a feature, and maybe I just go ahead and rename it to COG distance. Alright. You should also see that it will create a distance parameter for you. So if you want to know what the current distance is, you would go here to 3 columns, feature parameters, and just type in distance. This is the name of the parameter that we want. So it will show you what the value is between those two point on the plane. Anyhow, so our idea is to basically minimize this particular distance to be 0. Alright? So in order for us to minimize this distance, we might have to change a certain dimensions per se in order to move the center of gravity. Okay. Now there are many dimensions in this particular assembly. Which ones do I pick? And if I say I want to pick a certain dimension, what should be the range of that particular dimension within which I want to vary it? Right? So what you can do right now is run a sensitivity analysis. So in a sensitivity analysis, you would select a dimension. So you click here, pick a feature, and say, I want to vary this dimension right here, 72. So I want to vary this 72 dimension, the angle between 60 and 85. And the parameter that I want to plot is the distance parameter. So I want to see when I change this particular dimension over this range, how is the center of gravity the center of gravity position going to change? Number of steps, I'm going to just use 5 and say compute. So now it's going to throw you this little graph which tells you that as the distance changes from 60 to 85, you can see that distance value is very less at around 78 or 79. Now, why is the center of gravity very important? The reason it is important is that if I run an optimization, say I want to optimize this value such that the distance is almost 0, and if I choose a range from say 60 to 70, I would never get that value because see the value that we want is around this range. So by running a sensitivity study, I actually am able to figure out, should I use this design variable in my optimization? 1. And 2, if I'm going to use this design variable in my optimization, what should be the range for it? Okay, so you can see how it shows you as you change this design variable value over a certain range, how your different parameters change. Now, next thing we're going to run here is an optimization. So here I can run a feasibility study where notice that the system just evaluates different possible designs, or I can run an optimization. Notice it finds one proper design. So you can see that the goal is kind of grayed out because there is no such goal. You're just trying to figure out if it's possible or not. Okay? In an optimization, you have a certain goal. So let's say we want to add a constraint. We're going to say this distance between the point and the plane, I want it to be equal to 0. Alright, and then we cancel out. Now things that I want to vary are my design variables. So I want to change a certain dimension. Say I want to change this 72 dimension. I want to change it from say 75 to 85. I want to add another dimension, say this one. I want to vary that dimension from say 16 to 20. So note that I can pick multiple dimensions and vary them. You can see what each dimension does. I want to vary that from say 26 to 20. Notice these ranges were obtained by running sensitivity studies, because in here we saw the answer was close to 79. If I ran this analysis with say a range from 60 to 75, I'll never get an answer. So by running a sensitivity study, I know if I should use the design variable or and also what should be the range of it. So when I go ahead and hit compute, sorry, this needs to be 30. I'm going to hit compute. It's going to go ahead and optimize this particular bicycle for me, and it's going to show me what the feasible solution is. So you can see the feasible solution right here is 16.03. The angle value is 77.39, and also this particular value, which was 27, is 26.03, and the distance, you can see it in the model tree right here, and the distance is 0.00. Okay. Now, one thing that you can do is you can just close it. You can confirm to keep the values, or you can undo to not use the values. You see the distance changes back. Now, while you run this particular sensitivity or feasibility study, you can see that in the options, you can choose to show different graphs. So I want to show the graph of the constraint. I want to show how the constraint goes down as we run this optimization. So I'm going to check that and hit compute again. Give me a second, and you can see that it kind of shows you how the constraint is converging with respect to your optimization. Okay, so you can get all these graphs. So you can say close and confirm, and you can now see that the center of gravity distance is where we want it to be. All right. So this is behavioral modeling. You want to design your model such that it behaves in a certain way. Now, another use case for this is, say, for example, we are designing a crankshaft, and we want the center of gravity of the crankshaft to be right on the rotation axis. If it's not, when the crankshaft rotates, it's going to induce a moment about the center of gravity position. So it's better if the center of gravity of that crankshaft lies exactly on the axis of its rotation. So we can go ahead and run a little math where the center of gravity is, then find the distance between the center of gravity and the rotation axis, and try to change various dimensions in order to minimize that distance to 0. So that's another use case where you can use behavioral modeling for, say, moving parts. So next thing that we're going to talk about is some of the analysis capabilities that we have with respect to BMX. So you can see fuel tank example right here, and I want to know the one-sided volume and pick a plane. So that you can pick different planes. So right here, everything above the plane, that's the volume. You can flip it down and say that's the volume. Right? Now, where can we use this? We can choose to minimize or maximize this volume by moving this plane up or down. So in this way, you can say get a marker for, say, okay, half the tank or 3/4 the tank or quarter the tank, right? So you can move this plane and measure out what level is half of the volume or quarter of the volume. So here's an example for one-sided volume. The second thing we're going to talk about is, all right, so now that I know I've designed this particular fuel tank, I want to know what the volume of the fuel tank is, and I want to know what I can change to minimize or maximize the volume of the fuel tank. So what I'm going to do is I'm going to go right here and insert. So you can see this is completely solid. There is no shell's been suppressed. So I go ahead and run a mass property analysis. Now in the mass property analysis, I'm going to save it as a feature, and I call it solid volume. Right? And then you can see that it will automatically create a volume parameter for you. So I go ahead and add it. So how do I find out what the volume parameter or what the value of the volume is? I can go to tree columns, feature parameters, and type in volume. So here I have the current volume of the fuel tank. Now I'm going to shell it, and now I'm going to rerun the mass property study, and then I say feature, and I call it shell volume. And you can see that it will create a volume parameter for the shell volume feature. So you can see the volume of the shell. Now this volume is the volume of the material left. So by doing solid volume minus shell volume, I'll get the volume of the empty space. In order for me to do that, I'll create an analysis feature, which is right here. Now, let's say fuel. Okay, that's the name of my feature, and I'm telling that it is a relation, and I hit next. Now in the relation, this is how I'm going to read it. Say volume colon FID underscore fuel is equal to, so the way I'm reading it is volume parameter of feature ID fuel, okay, is equal to volume parameter of feature ID solid volume minus volume parameter of feature ID shell volume. Okay, so volume colon FID underscore shell volume was the name of the feature. So you can see that is the volume of the empty space. Now here there is something called feature ID and feature number. So if you go look at feature ID and feature number, you see that the feature number is just a serial number 1, 2, 3, 4, and this is the feature ID. Note that when I write my relation, I'm going to do an edit definition right here. Quickly go back to the relation. Now instead of writing solid volume as a name right here, it would be better if I put 8480. I put its feature ID instead of its name. Why? Because I might go ahead and change the name sometime in the future, and I don't want my relationship to fail. By calling out the feature ID never changes. You can change the name to whatever you want, and your relationship will not fail. Okay, so you can either call out the name or the ID number. So here we have the volume of fuel. All right, now again you can go ahead and run some sensitivity analysis and say, okay, I want to change this dimension, which is the thickness. I want to change it from 2.25 to say 3, or say 2 to 3, and the parameter that I want to plot is the volume of fuel. I want to run it in 5 steps. So you can see as the thickness increases how the volume of your fuel tank changes. And if I'm looking at an answer where I want the volume of the fuel tank to be exactly equal to 33,000, so you can see, I'm sorry, 330,000, that's around here, right? So it's between 2.55 and 2.65. Enough? So that's what my sensitivity study gives me. I can go ahead and optimize, where I say I wanna minimize the volume of the fuel. I wanna say the volume of the fuel needs to be 330,000. I want to say the dimension that I want to vary is that I want to vary from 2.55 to 2.65. Compute. So the smaller the range, the quicker the optimization. So if I close it and confirm, notice it tells me that's pretty much what my volume is. Now you see that you can increase the accuracy level of your part and you can get to more zeros, or get closer. You can increase the percentage of conversion of your optimization to avoid any kind of errors like these. You can go ahead and say, you know what, I want to have a percentage of convergence of 1%. So allowable error is 1%. So it's going to get much closer to 33,000 exact. So anyways, that was volume analysis. Next thing that I want to talk to you guys about is the one-sided, I'm sorry, we already got through one-sided, section mask properties. So if you create a cross-section, say for example this little heat sink, and I have a cross-section created right there. So that's my cross-section, okay? So when you run mask property analysis, you can dig in this particular tab and say section mask properties. And here you can choose to use a datum plane, say top plane, or say the front plane, and you can see that you can choose different planes, or you can also use the drop down and pick your cross section. So that's my cross section, and it tells me the area, center of gravity, moment of inertia, all those details right here. And I can click on this I, it kind of comes out here, and I can also go ahead and save it as like a DAT file, right? So you have your cross-section mask properties that you can look through. All you have to do is kind of dig here and find that. All right. So next thing we're going to talk about is clearance. So let's look at a pairs clearance example. So I want to know what is the clearance between two parts or two surfaces. So I'm going to go ahead, get the features shown up in the model tree. Go to analysis, and right here you have global interference, volume interference, which kind of tells you, you know, is there anything else interfering with the closed quilt? You have global clearance, where you can check clearances or interferences between parts of any two surfaces in assembly, or you can do pairs. You just pick a pair of parts and see what's wrong with that. So right here we can go ahead and pick surfaces. So I'm going to use my smart filter and go ahead and pick surface. So I picked two surfaces. Notice that there is positive clearance. That means there is no interference. Okay. You can go ahead and save this as a feature. You can call it surface clearance. And then I want to also check this box, which creates a parameter for me, which is called interference status. Okay, interference status. So now I can go to my tree columns, feature parameters, and say show my interference status. Notice the interference status is 0. Now similarly, I can go to pairs clearance. I can pick parts now. So I can say part. I'm going to pick this part. I'm going to pick this part. So you can see there is 0 clearance between them, and it also tells you the volume of interference between them. You can save it as a feature and say bolt clearance, and we'll choose to create an interference status parameter. So you can see if there is interference, the value is 1. If there is no interference, the value is 0. So you can do that between pairs of parts or surfaces to do this. All right. So next thing that we're going to talk about is the Creo simulate, motion analysis, Excel analyses, performance monitoring, and then some optimization and sensitivity. Okay. So let's start off the Creo simulate. So here I have a little part. All right. So I'm going to go into application simulate. I've already run an analysis. I'm not going to run it again. So just want to show you guys that those two surfaces right there, those two are fully fixed, and I have like a bearing load applied right here. See that? It's a bearing load. Now, I already ran an analysis, so I'm looking at the result for this. So let's say deformed shape and show me the stress. So you can see what the stress value is. It says 1.27. That's the maximum one meter stress. Right? So we have this little FEA done on this model. Okay? So once this part's done, we can get into BMX by going to the analysis. We say we want to run a simulate analysis. Simulate. Notice that if there are any predefined analysis, it's going to show up right here. We can compute. So it's going to come back and show me all my different parameters, maximum displacement, maximum one meter stress, etc. I can save it as a feature, say structural, save it. So there you have it, my analysis. You can close this. Now, analysis feature, you can go here and say, give it a name, say it's a Creo simulate analysis, regenerate always, next, you can compute so that you have all your values done. Close this. So notice that it's going to ask you to create a parameter for these things. So you can see you have total cost, total mass, maximum displacement right here, maximum one meter stress. You can choose to change the name over here. You can choose to change the name to whatever you want. All right. So it's creating a parameter for that. I'm going to say done. So what is the one meter stress? So go to 3 columns, feature parameters, add that, and that's the value of one meter stress. So now if I edit and change that value to 60, you can see my one meter stress changes. Right? So now I can run a sensitivity analysis where I'm going to vary that 60 dimension from say 45 to 65, and I want to plot the maximum stress one meters. I will run it in 3 steps. So it should go ahead and show you a graph where it shows how the one meter stress is going to change as you change the value of that. You can run it with more number of steps to get a more curved graph. All right. So this is how you can use pre-run simulate analysis and kind of use to see how these changes that you're going to make are going to affect your particular stresses and displacements and stuff. All right. So next, after this, what we are going to talk about is something called an Excel analysis. Okay. In an Excel analysis, I'm going to use like a wing part. All right. And I'm going to show you as to when I change the angle of attack, okay, what is going to be the lift force acting on this. Okay, so I have like an Excel calculation, Excel sheet done where I'm going to just show you how to use that particular Excel sheet. So here I have area measured, so area of this part projected onto this plane.
Welcome to GoToWebinar, web events made easy.
This parameter has been created, and I can use the 3 columns feature parameters and use this projected area to calculate what it is. All right. So now I'm going to go ahead and edit. Say I want to edit that value to 5, and you can see how the projected area changes. Okay. All right. So that being done, I'm going to go ahead and click on the analysis feature. You can give it a name, say Excel. Say it's an Excel analysis. Say next. You can choose to load a file, and I'm going to load the Excel file. It's going to open up the Excel file right here. So you can see there's a lift coefficient, there's a wing speed, there's an air velocity, there is an air density, there's a projected area, which we will be sending it to this Excel file. There'll be an angle of attack, which we will be sending it to the Excel file. And this uses this particular calculation and tells me that's how much the lift force is. Okay. So what I'm going to do now is I'm going to map the dimension to the Excel. So I'm going to say dimension. I pick that dimension 5 and say this dimension 5. You see this little menu manager. It's still, we still have the menu manager. So we're going to say this is going to go here. See that? So E16 cell. You can see that right here. It says E16. Now I want to add a parameter, which is the projected area. See that? 125. I'm going to say OK. And that projected area goes right here. And I'm going to say done. So it's going to add those two. Now output, what I want to read is this. See that? That's what I want to read. Now compute. So that's the value right there. Okay. Say close. You see that gives it a name, Excel, third column, 7th row. I can go ahead and call it lift. Yeah. And say done. Now we can go back to our 3 columns, feature parameters, and type in lift. So there you have your lift. So if I go ahead, edit this value to say I want to go 15 degrees, like that. You can see how your lift and your projected area changes. You can go ahead and make it 10 degrees. And you can see how your area and your lift force changes. Right? So we can use Excel file to kind of determine a lot of things within our design. Okay? So that was Creo Simulate and Creo Excel analysis. Next thing I'm going to talk to you guys about is the performance monitor. So performance monitor is where you can look at a particular parameter and say, hey, is this within the specified values that I want it to be? Okay. So let's look at performance monitor. So here I have a little assembly. If you watch my MDO example, this was there. I used this particular example. Now you notice that I've created a motion analysis right here. That motion analysis, and I'm going to show you how this was done. So you can say next. See, you have a drop analysis right here, and you go ahead, run it, and it shows you how the cams kind of slip. So we have a motion analysis which say minimum and maximum are around 4 and around 11. Okay. So how was this done? So let's go back and actually go into mechanism. So here notice I have a cam connection between this part and this part. And I'm going to go ahead, select the cam, do an edit definition. You see? There's a cylinder surface, and then there's the base surface, and here I'm saying enable the lift off, and that is the static friction and kinematic friction values. Now I'm going to run a dynamic analysis and say run, so you can see how it slips, right? Now, so this is my particular analysis. I'm going to close this. I'm going to go in here to analysis, and let's say call it motion. Say it is a motion analysis right here. Say next. So notice that from MDO, it finds out that you've run a drop analysis. Run it. It's going to run it in the background. And you can close this. So you see different parameters that you can create. Okay. So that's how this particular analysis was created. Okay. Motion analysis. Here are some of the parameters that we have. We're going to run this, and it kind of shows you the up and down. So with respect to performance monitor, now let's say we want to monitor the cam slippage maximum value and the minimum value, right? So now I'm going to say done. Right here you have performance monitor. So I'm going to click on that, add a parameter. So notice, because there's only one analysis run and it has two parameters within it, minimum cam slip and maximum cam slip, only those are shown. Otherwise, you'll have a drop down right here and you'll have multiple analysis if you have multiple analysis. So notice I want to go maximum cam slip value is 10.39. Now I can say less than, equal to, less than, whatever, and say reference value. I can enter a value or I can use a parameter value. Okay, so I'm going to say 10 right here. Tolerance. Now I say I want it to be within an absolute value of 0.4, for example. Okay, you have, and you have your warning. If I say tolerance, I want it to be within 1%, I'll say 1 and a percent. See what I'm saying? I can put a percent, say motion, say it's a motion analysis. Next. So you can see it's going to calculate the distance, it's going to calculate the clearance, those two values. You can see how the clearance goes up and down. And this one's clearance, maybe make this smaller, and this one's for clearance and one's for the distance, that distance. Now this distance is the distance from here to here. Clearance is the clearance between these two parts. All right, so you can say close. So notice that, do you want to find out what is the minimum distance between them? So say yes. See right here. So minimum distance and maximum distance. And then I want to know what is the minimum clearance between those two parts. Clearance. Right? So we can always go 3 columns, feature parameters, say minimum, clearance. It tells you what the clearance is, okay, between those two parts, so that this doesn't come and interfere with it. All right, so now this is done. What I want to find out is I want to run a sensitivity study. Okay, in the sensitivity study, I want to go ahead and find out what happens to certain parameters, like say the volume of water that I'm going to suck in every time I'm going to like use this pump. And see how I can maximize that. So let's look at 3 filters, get the features in. So we have height and say clearance. Let's do the volume calculation. So see that it's a relation. And what I've done is I'm trying to say the maximum distance y minus the minimum distance times pi. It gives me the volume between them. See right there. Okay. So have that volume. So now I want to run a sensitivity analysis. So sensitivity analysis, the dimension that I want to change is that, see that, the length of that link. I want to change the length of that link from 6 to 10, and I want to see how my volume right there changes. I want to change it in 6 steps. So you can see as the length of that link increases, the amount of volume kind of goes up. Okay. Similarly, instead of just the length, you can also choose to say, I want to increase the length of the handle. Yeah. So I want to change that length of the handle from 18 to 22, and I want to compute that. So you can see as the length of the handle increases, you can see that the volume decreases. Now, similarly, we can also figure out, see that's the distance where the link get attached to the handle. So I'm going to select that dimension right there, 7. Enough, 7 dimension, and I'm going to vary that 7 dimension from 5 to 10. So you can see as the distance increases, as the 7 dimension increases or this link gets pushed out, you see the volume increases. So you can see how different dimension changes affect your goal, which is your volume. Okay, so now that we figured out these things as to how the certain design variables are affecting our design, we will go ahead and say, hey, you know what, I want to go ahead and kind of like run optimization, right? I want to optimize this particular form so that it gets maximum amount of water in there. So I'm going to go ahead and say optimization. I want to maximize the volume. Okay. Now, constraint that I'm going to add is that I don't want any interference. See that little clearance between this part and this part? I'm going to say that clearance should be more than or equal to 0.25. Okay, that's what I want to stay at. So that's my clearance value, and then I go ahead and use my dimensions that I want to change. So I want to change that between, say, 6 to 10. I want to change the length of the handle, 20 dimension right there. I want to change it from 18 to 22. I want to change the position of the link from, say, 5 to 10. So those are the 3 design variables that I'm trying to change. And I'm going to hit compute. So now it's going to try and change these design variables, maximize the volume, and also try to maintain the clearance value to be greater than or equal to 0.25. So here's a optimization graph. Now we need to make sure when we look at an optimization graph that it actually like kind of asymptotically reaches like a straight line, and then we kind of know that, hey, you know, it converged well. So it's still running the analysis as we talk. So now, once we get done with the optimization, we can choose to say, hey, no, I want to keep this, I don't want to keep this, or whatever you want to choose to do. Okay. Now, like I said, we only kind of like scratched a little bit of the surface in terms of behavioral modeling. It can do much more, or different types of analyses also with this. So I would stop right here and then kind of like, you know, leave enough time for any questions we might have. And you can see how the graph kind of almost reaches a straight line. right? That's what we want to see, where you say, okay, this analysis has converged. Now, for this optimization to be successful, the most important thing is the sensitivity study. And also definitely modeling practice, because when you change a value over a range, you don't want things failing on you. And so by running the sensitivity analysis, I could get a proper range for these design variables. So when I say close and say confirm, it keeps the new design variable values and kind of like changes them. So you can see that value went to a max of 10. This value went to 18.114. This value is 9.39. All right. So if you do an definition right here, so you see you can go ahead and kind of show the 3 columns and say volume. So we can see the volume is so and so. And we can also look at another parameter, clearance, and see that's the clearance value that we wanted. All right. So that will be it for this. There is much more. I hope when we do another one of a BMX, I'll be able to show more things like, say, electrical clearance right here. I can show a more multi-objective design study. We can do some statistical analysis. We can do tolerance analysis. Maybe we can add in some math CAD analysis to it, right? So we can do many different types of analysis with BMX, and we'll probably do it another time. All right, Rosalind, are you there?
Yes, I am.
All right, do we have any questions?
I don't see any yet.
All right, so you guys can shoot away with any questions you might have. If not, then that's pretty much it.
And you can always send questions to me. You can reply to the registration email of this webinar, and I'll be more than happy to get any of your questions over to Sukumar. And he's about to put his email address up for you as well. We do have a question. Is BMX necessary to optimize simulate?
No. You can do simulate analysis or optimization and simulate without having BMX. I'll put my phone number, but I don't know, getting calls at 10 o'clock in the night from China, so I wouldn't do that. But you guys can always email, and if you have a question that we have to talk on phone, then I can always give you guys a call. All right, Rosalinda.
Okay,
that's it.
That'll do it. And I'll make the video replay available this afternoon, and I'll shoot it out to everyone.
All right, thank you guys.